Okay, so the addition rule, what in the world is this? And we're going to talk about something called overlap in just a bit here. With it. Everything here. So let's jam. First things first is this little definition right here. Something to be mutually exclusive for the addition rule. So if things are mutually exclusive, which means two events are not occurring at the same time. It's impossible for them to occur at the same time. So you could say it one way. You could say two events A and B cannot occur at the same time. You could say A and B have no outcomes in common. So again, this is all just build up. Finally get to the addition rule. If you're to draw this out, which is this guy named Venn, V-E-N-N, he made these little diagrams to think about stuff, how things are related to each other. So the box is called the universe, and A and B are the different subsets. So if you want to kind of draw it out, that's fine too. If you want to have visual illustration of it. So there it is, A and B. Notice they have nothing in common. Those things are mutually exclusive. If you have one, you are not going to have the other. Then you have sample spaces or universes where things are in common. So notice the little overlap there. A and B have something in common. Therefore, these guys are no longer mutually exclusive towards one another. So let's go and talk about this. What are stuff that's mutually exclusive? Things that are not. Let's jam. All right, so let's do this here. Determine whether these events are mutually exclusive or not. So event A, you roll a 3 on a die. Event B, you roll a 4 on a die. Mutually exclusive events. Okay. Let's see. Right. For the first event to occur, which is 3, right? These guys cannot occur at the same time, right? If you roll a die, you get a 3. There's no way you could be rolling the same die and get a 4. That does not make sense. I think the first and second kind of confuses us, right? As opposed to just like, can they occur at the same time? Yes or no? Okay, how about this one? Just shout out. I'm accepting shout outs here. Mutually exclusive or not mutually exclusive? We have overlap. I agree with Tristan. Not mutually exclusive, right? Can you have a male student that's also a nursing major? Absolutely. So there's overlap, not mutually exclusive. Sweet. Okay. So mutually exclusive or not mutually exclusive? Oh, let's do this. Show of hands here. Raise your hand if you say yes, mutually exclusive. Absolutely. Cool. And show of hand, mutually exclusive. No way, not mutually exclusive, because you can have one and the other at the same time. So randomly selecting a blood donor with the type O blood, randomly selecting a female donor. I think we can have a female donor that is type O blood, right? So there's overlap, not mutually exclusive. Sorry for the derail. Okay, with that said, let's jam with the addition rule. Here it is. This is how we can add things together. So we had the multiplication rule last time. Now we're tacking on the addition rule to see what this means. So probability of A or B happening. So if events A and B are happening, it doesn't matter if A or B are happening. What we can do is we can figure out the probability for A. We can figure out the probability for B, but then we have to subtract the overlap between the two. Let's see some examples here. Okay. And then we have this little disclaimer right here. Just, but if they're mutually exclusive, there is no overlap. Then that last part is technically 0. So we can actually just figure out the probability of A happening or B happening by just adding up the. Okay, so this one actually kind of works backwards and forwards. You can find out if something is a mutually exclusive event if things add up correctly. You find out if something is a non-mutually exclusive event if things don't add up well. Or you have this little overlap that you're not accounting for. All right, let's cheat on here. So let's go back to our cards. Cards here. So sorry, writing stuff down. All right, so for in general, when we add up probabilities, we have to account for the overlap. That's kind of what this is saying. If you know something is mutually exclusive, forget about thinking about the overlap. You can just add the probabilities together and you are good. It just means that if you do 2, 3, 4, 5, 6, or 7 events, you can put them all together. So let's jam. Here it is. You select the card from a standard deck. Or card stuff again. Find the probability that the card is a 4 or is an ace. So real quick here, before we do anything, think about this here for a little bit. Think back to our notes here. So how many? We have 4 different suits, right, in cards? 4 different suits. They go from king, queen, jack, and then it goes 10, 9, 8, 7, 6, 5, 4, 3, 2, and then there's aces, right? Each suit. So find the probability of finding a probability that the card is a 4 or an ace. So you find this one or the other thing. It doesn't matter which one I find. So how many cards in the deck again? 52. How many 4s are there in the deck? 4 of them, right? There's 4 for each suit. How many aces are there in the deck? 4 as well, right? There's 4 hearts, 4 clubs, 4 diamonds, and I always forget the last one. I think it's spades, right? Spades. Okay, cool. So let's see if this makes sense. So are these guys mutually exclusive? Absolutely. If you have a 4, you can't have an ace. You pick up a card. So I have 4 of these guys, and I have 4 of these guys. So if that is the case, let's see if this makes sense here. Just the way we would write it out, let's say probability of 4 or ace. Because it's mutually exclusive, I don't need to think about the overlap at all. It's just going to be the probability of a 4, probability of getting an ace. And what I'm going to do here, I'm just going to add them together. This is the addition right here. Right, some people writing it down, go for it. If you need to write it down, absolutely, that's good. This is for it. You just say, got this, makes sense, and we'll keep on going. That's cool too. break a little bit from the lecture so that, because I think it makes sense to sort of think of this. Let's do that. Let's go. I'm going to write this in as. You roll the dice. You will die. That is the one, right? I will that you will get a 8 or a 6. That's one. What's the probability you get that? Remember, let's kind of think back. So we're here in here. So the multiplication principle said if I roll this twice, right? I roll this twice, I just multiply the probabilities together, right? The addition property says, what happens if I have a combination of things that I want out of this? Okay, so talk to me here. So probability of 5 or 6. First of all, mutually exclusive or no? If I roll a 6, at the same time, could I be rolling a 5? Nah, impossible, right? I only have one dot in front of me, right? So mutually exclusive, that's fine. So probability of rolling a 5 plus the probability of rolling a 6. What is the probability of rolling a 5? Let's go with it, right? A single die has 1, 2, 3, 4, 5, and 6, right? 6 sides. Standard, right? Not the one that has 10 and 12. So for each one of these, is the probability 1/6? That's 1/6, that's 1/6, that's cool. So then for getting a 5, the probability is 1/6. Getting a 6, probability is 1/6. Adding those up together and eventually simplifying out, I got myself a 1/3. Okay, we did. Number 3, this is kind of what I wanted to show. So roll a die. You guys do this one here. Probability. Will get a, oh, let's go on. Let's do this one here. How about 1, 2, or 3? So before we do anything else, real quick, let's think to our heads here. What is the probability of rolling a 1, 2, or 3 on a 6-sided die? It has to be a half, right? Because you're accounting for half of them already, right? So that totally makes sense. Now let's see how mathematically it makes sense, right? We have to somehow do that 1/2 mathematically. So probability of 1 or 2 or 3, which means probability of 1, probability of 2, probability of 3. Okay, mutually exclusive, right? Cool, cool. This is 1/6. That is 1/6. That is 1/6, and that together gives us 3/6. And are we at 1/2? Absolutely, that's cool. The addition property works nice. The addition property does give us that little value. Okay, we're good. Okay. Now the fun part. Okay. You roll that. Find the probability of rolling a number less than 3 or rolling an odd number. Okay, we just have this as a number. Go back to 2. We got ourselves in trouble. Because again, we're trying to figure out the exact probability of stuff. And probability, what it started with initially was gambling. So it was people that were gambling. They were trying to figure out how to get their odds a little bit better at winning, right? So the question is kind of like almost like, would you bet on this or not, right? Anything that's above 50%, at least you have your chance of betting. If you're below 50%, you probably don't want to bet on it. So the question is, do we want to bet on this guy or not? Find the probability of rolling a number less than 3 or rolling an odd number. You guys talk to me. Mutually exclusive or not? Can you have those things happen at the same time? Yeah, there's some stuff here that's happening at the same time. So Mr. Vin or Dr. Vin with his diagrams kind of help us out here. The question is, can I figure out this piece right here? If I roll a die, and if it helps you with it here. So we have the odd number here. We have the less than 3 over here. That's what we want. We're trying to figure out if there's any overlap between the two. So let's see, number less than 3. So I have 1. Less than 3 would be 1 and 2 only, right? An odd number, all the odd numbers on the dice are 1, 3, and 5. So notice this is the overlap. 1 is actually overlap. And then the ones you can't be are 4 and 6. And they're actually outside of our 2 circles. So there's an overlap of 1. Good there? So now let's jam with the math behind here. So if I do this, so P of less than 3 or odd number. And the diagram kind of helps us a little bit here as well. So let's see, P for the probability that something is less than 3. Well, we know over here, there's only 2 numbers here, right? 1 and 2. 1 and 2 are numbers that are less than 3. So I have 6 different probabilities. That means 2 out of the 6. I have 2 out of 6 that's possible for that to happen. Are we good there so far? Okay, how many odd numbers are there on a dice? 3 of them, right? 1, 3, and 5. So there's 3. So that means getting an odd number would be 3 out of 6. And then what we do is we subtract out the overlap that's here. And overlap is just a single digit called 1. In order to get a 1, it's a 1 out of 6 chance I get a 1. So we got 1/6. So how about 2 plus 3 is 5, minus 1 is 4. So 4/3. If you want to write, 4/6. If you want to write down 2/3, that's fine too. 2/3 is the perfectly correct answer. If you want to write down 0.667, that's fine too. 0.6 with the bar on top of it like this for repeating forever, that's fine too. Any one of them is fine. Okay, so here it is. When we think of probabilities, we always have to think about the overlap that's happening. So we're not over counting something. If we did it without considering the overlap, we would have been at 5/6. That's kind of overlap. Okay. Are we good there with addition? All right, let's jam. Now let's get into frequencies. Let's go with this. Okay. Frequency distribution shows volume of sales in dollars and the number of months in which the sales representative reached each sales level during the past 3 years. So I'm thinking there should be 36 points over here. All right, using this sales pattern, find the probability that the sales representative will sell between 75 grand and 124 grand the next month. This piece right here, pretty sure. Oh, it's this one and this one. Is that right? Sorry, go back over here. 75 is right here. 100, almost 125,000 is right here. So it's these 2 brackets or sales brackets. Right? So what's the probability of event A happening and event B happening? Just making sure, right? This is called empirical statistics, right? This is like we're giving data from the field, right? This is not like rolling a dice, right? This is not like picking up a card, right? This is something called real statistics, right? Or empirical statistics. Getting data from the process that's happening. Okay, so let's talk about this here. So first things first, is this mutually exclusive? If he had $999,999, would he be in one category or two categories? He'd be in one, right? They're mutual. There's no overlap between these categories, right? So any overlap? That's cool. So here it is. If you did want to draw a Venn diagram, it would look like this. So now the question is this: what's the probability of this happening? And what's the probability of this happening? And what do we do with those two numbers? Starts with A, addition. We just add them up. So let's go for it here. So anybody real quick? Count for me the number of months we're looking here. Tablet, how many is that right there? Make sure. Eight. That's 36, okay, just want to make a second. I hear a second on 36 and a 36, perfect, okay. So we have 36, what's the probability of this salesperson getting between 75 and 99,999? Isn't it 7, right? 7 out of 36, is that right? Talk to me, you guys are too quiet here. Let's see, what's the probability or the fraction of him falling into this right here, into this category here? It'd be 7 out of 36, is that right? Mm-hmm. What's the probability of him being in this category? 9 out of 36. That's cool. So let's go with it here. So probability of A happening or the probability of B happening, there's no overlap. So it's just the two probabilities multiplying together. And I don't know why the author keeps it like this, 16 over 36, because we can reduce those. So by 4, so before 4 over 9. If you want to write down the final terms, 4 over 9 or 0.4. Get just this whole concept of the addition property. And this one is actually talking about empirical data, not theoretical data like that, the dice or the cards. Okay, let's get a little bit more complicated. Not by much. Here it is. This is where you guys talk to me. Are we okay with this problem? So we had a range of data. Is that right? Ranges were mutually exclusive data. We had the number of months totals. The probability was 7 over 36 for category 1, 9 over 36 for category 2. Additional property says we just add those guys together to give us the probabilities as a whole. Okay, a little bit more complicated. I think you guys can still handle this stuff. Okay, so blood types. Remember how we talked about blood types? There's blood type O, A, B, and then AB. And then each one of those could be either positive or negative. Anybody know what blood type they are? Raise your hand if you know what blood type you are. I don't know myself.
I just know I'm O something. I just don't know if it's positive or negative.
Gotcha. Okay. Oh, something or other. All right. Okay, so blood bank catalogs the different blood types, including whether it's positive or negative, given the donors during the last 5 days. That's cool. Number of donors who gave each blood type is shown. Okay, let's see what we got here. Find the probability that the donor has type O or type A blood. So we don't care if it's positive or negative, right? And we want to find probability of probability that he walked in, he has O or A. I think it's the addition, is that right? I'm thinking if you're just talking about, we don't want the positive or negative, right? Remember the ones that we did before? They were called conditional probabilities. Remember those? It says, find if it's positive if it's blood A, right? We're not doing that. This is much simpler than that. So type O blood, right here, grand total is 184. Type A blood. So what's the probability of just being type O blood? What's the probability, not the total? It'd be 184 over what? Yeah, and the 409, it's this little total over here, right? That's the probability. What's the probability of type A blood? 164 over? Still 409, perfect. Okay, oh, real quick here, before we do that, next thing is those two blood types mutually exclusive? Yeah, it can't be two different blood types, right? You want to be one. So yes, they're mutually exclusive. That means the addition property says, just add them up. So type O or type A, addition property says add the probabilities up and you're good to go. It'd be 184 over the total. And be 164 over total. Add those up. That's pretty big. Notice that type O and type A, they are the most popular. I'm not sure if this is true stats. I think what type O is actually not as popular. Can we agree?
Yes.
Okay.
I think it's one of the more rare ones.
Let's write that too, yeah. Okay, let's get a little bit more complicated. And you guys will be experts reading these charts here. Again, this is just probability stuff. Jim, let's go to the next one here. Ooh, you may just not be mutually exclusive. Let's see, find the probability that donor is blood type B or is just a negative blood type. That's it, which is still important. Ooh, question, is there overlap now?
Yes.
Yes, can we actually find the overlap? What's the overlap on this guys? Give me the number. Give me the number that gives me the overlap. It's the 8 right over here. Absolutely, right there and right there, huh? It's this, the B type and then the negative type. So there's an overlap. So if we're just going to do the addition property without subtracting this guy, we would be overcounting the probability, which is not good. Because we want our probabilities to match well. Okay, so not mutually exclusive. Overlap is this little 8 right over here. So now let's do the math behind it here. So we're going to figure out blood type B. Notice this guy comes down, right? Look at this. Blood type B comes down here, right? It's this guy, right? And we already said it's over the total, right? So let's go with it here. Let's do the math behind it. Here it is. So it's blood type B or blood type negative. Now the formula is like this. It's blood type B plus blood type is negative, subtract the overlap between the two. So notice it's always the totals for all the columns, right? It's the totals here. Blood type B is 45 over the total, which is 409. Then you have the negative side, which is the total. All the negatives are 65 over the grand total of 409. Overlap is just that little 8. Those 8 people divide out 45 plus 65 is 110. Subtract 8 makes 102. About a quarter of those people. So you should expect a quarterly income. So this is kind of what these are built, because if you have a, let's say you have a certain blood type, and we know from the blood banks that a certain region of the country may have more than one, more than the other, okay? So you would market, especially during that time, in that region. Or just market that. That's just total curiosity here. How many have given blood before? Okay. They never tell you which blood type you are.
They do, but
Okay, gotcha. Okay, so one of the benefits of donating blood is they'll actually tell you what blood type you are. Okay, did you do it here on campus?
always live in that ring, so we look for a city level.
Okay,
And we're looking to schools.
oh, sweet. Okay, that is awesome. Okay, perfect. Okay, guys, there's the addition property. You got to be careful for any overlap that occurs. So on the book or in the book, which is kind of cool. Summary so far is that we have the, remember, classical probability is things that we think about like rolling a dice or the cards, right? Empirical probability is actually things that are happening in nature or the sales guy that we just did, right? So this is probability is always between 1 and 0. 0 means it's impossible for happen. 1 is means it's going to happen. It's certain. Here's your complement. You subtract from 1 to get the complement of the other thing happening. And the multiplication rule given here already, as well as now the addition rule. There's two different kinds, right? Mutually exclusive and non-mutually exclusive. For multiplication rule, we got to think about is it dependent or these two wholly independent events. Okay, one more example. I think so, yeah. Now let's go one more example. Let's talk about football, just for the fun. So this is combining rules for probabilities here. This is the breakdown positions of 253 players, right, that were picked for the 2016 national draft. So by position. So how many of you guys talked to me here? How many quarterbacks were picked? Got 15 quarterbacks that were picked right here. Ooh, you know what? Let me see if I can zoom in. Oh, perfect. Ooh, okay. What's the most highest position that was picked? There's 34 of those guys. One more, right?
Oh, no,
Defensive end, that was the most. I know maybe the 2015 season, a whole bunch of them never retired, or they said bye-bye to them. Okay, so that's cool. So here's your different positions. Let's go back here. Okay, find the probability that a randomly selected draft pick is not a running back. That's weird. It's kind of like the not thing. Not a running back. Or a wide receiver. Oh man, this is crazy. Running back. Let's go running backs. Running backs are 23. Wide receivers? 31. Let's talk about this probability stuff. Okay. So, again, it's going to be kind of crazy here. Ready? Put your think caps on for a little bit. Define events A and B. So first of all, we're going to pick A. We're going to pick draft that it is a running back. Draft pick is a running back. Even though we said not in the beginning. It's going to be C. Then event B would be picking a draft pick that is a wide receiver. Okay, let's jam it. So first things first is if they pick a running back, are they able to pick the same wide receiver at the same exact time? I don't think so. Huh? Right, if you pick one position, you're not going to pick the other position. So in this case, these guys are mutually exclusive of each other. And so the probability of both of these guys coming true, everybody okay with 23 over 253? 31? 253 makes 54 to 253. That's cool, except one small problem. Our original task was not to figure out a running back and a wide receiver. Ours was not a running back and a wide receiver. Not first, need to. Okay, so now let's go to this one. By taking the complement of A or B, we can determine the probability of randomly selecting a draft who is not a running back or a wide receiver. So here we've got. So this is where the math kind of have to be a little creative how you want to get to the answer. Let me go back a little bit, just make sure we got this. Let me go back real quick up to here. So it says, find the probability that a random selected draft pick is not a running back or a wide receiver, right? Not this one and not this one. The easiest way to do this probability is to figure out, because these guys are mutually exclusive, a running back, picking a running back, picking a wide receiver are mutually exclusive. We add the probabilities together, and all we're going to do is we're going to subtract or make the complement of what we just got in the slide. So about 78% of the people chosen in the 2016 draft were neither wide receivers nor running backs. Of course, it gets more complicated than that. When you're up to the draft picks for NFL players, because yes, you do account for how many people are retiring, how many people are switching to a different team, how many teams need more, how many teams have weak positions there, right? They actually need a rookie to come in to see all that. But this has just been the basic stuff. All right, talk to me. Need a 10-minute break? Or you got to, we'll do hand raising of hands here. How many say 10-minute break or one going? Those are two options. Raise your hand for a 10-minute break right now, and we give 3.4. Okay. Raise your hand and keep on going. Good. 1-0. All right. One person voted. All right, let's jam for keep on going, one by one. Okay, and then we'll get out of here. Okay, I'm going to go here. I'm going to go 3.4. Okay. 3.41. Maybe like a few more rules here with probability. I think this is setting it up for challenge. Going down a rabbit hole. Getting a little more complicated as we go. It's not by much. Education is supposed to be easy, right? It's supposed to be educational. Like you have a textbook, right? It's listed into chapters, right? Those chapters are put into sections, right? The sections are put into topics. So it's kind of like trying to give you pieces of it at a time, as opposed to like learn all this. You could disagree with me, okay? So additional topics in probability, as well as counting, how we count stuff. Let's go. Two things we're going to study. These two things are called permutations and combinations. And then we'll jump in how it actually. So let's start counting first. How do we count? Objects that have to be counted. So one way to do it is something called permutations. Permutations means that there's some kind of order to the arrangement of these objects. The number of different permutations, number of ways you could scramble the order of these objects, is something called n factorial. That's what we say, n factorial. It's basically an exclamation point. So in mathematics, an exclamation point means You multiply that number times the one number lower than that number, times another number lower than that number, times another number lower than that number, all the way to the big number. I will have you calculate that at this point. Yes, let me see if there is a. All right, some examples. So 0 factorial, just going to be 1. That's the only extra little definition here. So somehow when you get a 0 in there, you just have 1. All right, let's some examples as we go. So 6 factorial means you're multiplying 6 times 5 times 4 times 3 times 2 times 4. And these numbers you can see multiply very, very quickly. All right, 4 factorial. Just another one to look here. 4 times 3 times 2 times 1. And obviously, 1, who cares about the 1, right? Because you're going to have 1 more times. Okay, cool. We got that. Now, really quick here, out of curiosity here, for a calculator. Let's see. Since we're going to get to these here, if you have your calculator in front of you, let's each one of these here. So in the calculator, you should have something called a map menu. So you have 2, 8, 3. You guys see a map menu? Raise your hand if you don't see a map button. Good. See a map button. Okay. We're going to click on the map button. Can you guys tell me what's on the front row headers over here on top? What does it say? Give me some letters there. What's the first set of letters?
N-U-N.
M,
N-U-N.
N, U, N. N. Oh, that stands for number. That's cool. Okay, next category. C, S.
X.
X. Okay, that's cool. Complex. Okay, next.
P-R-B.
E, R. Is that it? That's it, huh? Okay, we're going to click on this little category right here. We'll click on that. PRB. Then you have a number list now, right? 1, 2, 3, right? I think number 3 should be something that looks like that. Is that right? Or number 4? 4. Sweet. Okay. Okay, now practice a little bit. So now go to quit and get all the way back to the home screen. Quit button. It's the mode button. All right, we're good there? Everybody back on home screen? Sweet. Okay, so we're going to punch in the number 7. 7. That's the number 7. We're good? And then we're going to click the map menu. When you click the probability menu, we're going to go down to number 4 and click enter for this step. I'll walk by it as well. So we're going to, and then click enter again. And we should find Sweet. Something about 5,000 something or other. Is that right? Okay, you were wrong. So let's go 7. Let's go math menu. Probability. And click enter. And click enter again. Sure. We got it. You help her. Just got it. Yes, click enter. 7. Math menu. Probability. Down to 4. So there's 5,000. Okay, let's go 7. 7. Now go to math. You're just jamming. Let's go sit again. So 7. Math menu. Oh, sure. Okay, 3. Got it. Okay, 5,040 should be the end result, right? Okay, so we're gonna use those. So that means that would be 7, right? 7 items. And the different ways we can select those. Okay, what does this mean? Again, this whole concept of probability. We'll tie it all together. Let's jam. How many did you play Sudoku? Did you play Sudoku? Not enough patience to do that. And Sudoku is a grid in which what you do is you plug in numbers so that the numbers add horizontally, add vertically, and add at least diagonally across here. Diagonally this way and diagonally this way to be the same exact number. That's it. It's a crazy state. Now, this is very complicated because there's lots of stuff on here. But usually start off with just one of these guys, just a 9, 3 by 3 square. You say, hey, look, if I have 6, 7, 1 here, 8 and a 2, how do I make it so that I can put the remaining numbers here so that they horizontally add to the same number, which is vertically, which is bad. Crazy stuff. So if you're bored like crazy, just look up like simple Sudoku word and then see what you get. So the objective of a 9, well, this is 9. So 1, 2, 3, 4, 5. There's 9 squares going down. There's 9 squares going across. So this is an 81, right? There's 81 possibilities here. So the objective of 9 by 9 Sudoku number is to fill the grid so that each row, each column, and each 3 by 3 grid contains the digits 1 through 9. How many different ways can the first row of a blank 9 by 9 Sudoku be? Let me look at my first row. So this first row right here. What are the possible ways this thing can be filled? Well, let's see. How many numbers do we have left? We have 3 numbers left. Huh? We can even name them, right? Because I have 1 here, I have 2. I'm missing a 3. I'm missing a 5. And I'm missing an 8, right? Okay, cool. But if those numbers were not there, right? The number of ways this thing could be filled is there'll be like 9 different options for this one, right? 9 different options for this one. Oh, so 8 different options, right? Because once you use a number, you can't use it again. Hey, real quick here. Is this very much like the multiplication principle? Right, I think so, right? There it is. It's the multiplication principle all over again. So 9 possibilities for this first square, 8 for this one, 7, 6, 5, 4, 3, 2, 1. Now, when you're done with this, when you get 9 factorials in there, and see if you get the same number. Right. The reason if you have difficulty getting 362,880. Or you guys are experts now. Experts. Awesome. Checking. Giselle and doing. Good job, guys. Good. For Good there? Sweet. Okay. Jam. Okay, so that was just the beginning. Now let's jam. Let's bring this together a little bit into, so notice though, but some of them already filled up, right? Look at this, notice that some are already filled, just got this little piece right here that needs to be filled. So this is what permutations really are into. So let's do the equation first, then we'll get there. So here's what we do, you gotta type, we'll still use that. So permutation of n objects taken r amount of time. So So permutation means you're going to take n objects and you're going to pick out r of them at a time. So let's say for the first row, right, we had 9 different possibilities. But let's say you're only going to take 3 of them at a time. That's what this means here. Now the question is, how many different ways can I make that happen? There's an equation. Not highlighted, still want to write this in. So you got a small little n, you have a capital P for permutation, small little r equals, hey, there's our factorial stuff again. So that's going to be, look at this on top, it's n factorial, number of objects we have. On the bottom though, what we want to do is we want to subtract n minus r. So the number of objects we have, subtract the number of times we're going to take them. Okay, the only thing that we have to say is r has to be less than n, obviously, right? If you have 10 objects, you can't take 11 at a time. That does not make sense. I'll do some examples. Okay, let's jam. Let's try 2 problems here. Everybody got the formula? So here it is. Find the number of ways of forming 4-digit codes. It's kind of like your which no digit is repeated. So kind of a little different here. The multiplication principle says I can put down any number of what I like, right? This one is this whole concept of digit is not repeating itself. So they have to be unique. So once one is picked, you can't pick another one. That's the difference between multiplication principle and this principle. So let's jam. Let's see what this means here. So does this mean I'm selecting 4 digits from a group of 10? Is that right? I have 10 digits to choose from 0 to 9. I'm going to pick 4 at a time. And I can't repeat them, right? So once one is picked, I have to choose another one here. So here's how we do it. N is equal to 10. R is equal to 4. And before you start punching in the calculator, we'll just wait just a little bit. Let me give you the number for it here. So let's write this out first, and then we'll do something else with it here. So 10p4, or 10 permutation 4, is 10 on top, 10 minus 4 on the bottom, which technically is 6. And notice what happens here. I don't need to go all the way down. What I do is I go down from 10, I go down to my 6 factorial, stop there. Don't go any further because that 6 factorial on the bottom is going to wipe out the rest of it. That's weird. Remember how 7 factorial is the same thing as this one, right? Still get 40, 50. So the whole point is not to punch in 10 factorial top and then divide it by 6 factorial. If you want to do that, we can do that. So we good there? We just got what it looks like over here. Let's do this here. So on your calculator, can you do, let's do this first. Can you go 10 factorial, find the factorial button, right? Divided by 6 factorial. And of course, we should get 50, 40 on there. Goes without saying. All right, thumbs up if you got it. How about that? Should we get 55,000? Good, okay, got 2 thumbs up. Thumbs up, okay. And then, I'll meet with you, need some help. Okay. And then we'll do it another one. You guys can have a lot better. Good, yeah, Andy. Yes. Carla. Okay. Now, real quick here, before we move on. You guys ready? Now, go to your map menu. Actually, no, just punch in 10 first. 10. Very cool stuff here. Go to your map menu again. And then you go to probability over here, PRB. And once you click on it, notice what options do you have underneath there? And what? You have N, thank you, for RAND, which is random number. Number 2 is NPR. Hey, look at that NPR, number 2. Number 2. Click on NPR. And after that, what happens on your screen? Then it says NPR next to the 10. I'm getting there. Okay, then what you're gonna do before you click anything else, click 4 after that. And now click enter. Oh yeah, awesome. Okay. So this is NPR, is this little function right here. Good. One click of it, let's do the whole entire function. Okay, so let's do one call for you guys, go for it. Each year, 33 race cars start the Indianapolis 500. That's cool. How many ways can the cars finish first, second, and third? So what are all the different possibilities? And let's just try it. Go for it. See if you guys can do the NPR. And I'm going to walk around and see what you guys put in here. So 33 cars start. I want to know the combination of ways to get a first, second, and third. What should be the formula? Try yourself first. Think about it. Anybody got a educated guess? Is that hypothesis? Answer? How many are just filling in their calculators? Okay, let's go for you. Let's start. So think about this. Let's see if this makes sense. Are we selecting 3 cars, right? a group of 33. So that means our n value has to be 33. Our R value is just 3. And can you punch it into your calculator? So if you did it by the formula, you would punch in 33 NPR 3. If you did it by the equation or the ratio, you just punch in 33 factorial divided by 30 factorial. Any which way, we should get 32,736 different combinations or permutations of this happening. Okay, real quick here, I'm gonna put down my mouse here, and you guys try it yourself. Go for it. See if you guys get 32,736. Go. Yep. Check the possibility. Okay, was it easier doing the NPR function on the calculator? Yes, Mr. G. Thank you so much for showing that. Sweet. Okay, I think everybody did it by the NPR function. Sticks or not? Okay. Before you got it? Not before. By the NPR function, okay. Way easier. Isn't that kind of cool to have built-in functions into your calculator? Okay, that's permutations. Let's leave that aside just for a second here. Let's jam to something called distinguishable permutations. This means how many different combinations I can have. If they're just different types. Formula, there it is. Now this one, a bummer, this one does not have a calculator function inside your calculator. So this one we do have to go do it by input. So what we do is we just say, look, the number of n objects we have is n factorial on top. And what we do, we figure out all the different possibilities of each one of those on the bottom. So total goes on top, and then every single one of those types go on the bottom. Let's try an example. Still writing it out. Oh, sure, no problem. Okay, slow me down. Okay, we're good? We're good now? So let's try just an example here. So this is distinguishable permutations here. I got a building contractor. He's planning to develop a subdivision. And here's what we have. In order to comply with the code of how many stories we have in split levels. So he's going to build 6 one-story units. Or houses. Going to be distinct from another. 4 two-story houses in the subdivision. And also he's going to do 2 split level homes. How many distinguishable ways from the house is being made? And it's kind of saying this: if you have the first house is a 1-story, the second house is a 2-story, and the third house is split level, even though it's going to be the second 1-story and the first story, it doesn't make sense, right? It's still going to be a 1-story in the first level. So I want to get rid of the extra permutations of those. So let's see. Let's do this here. Let's label our values, because we have what? We have n, which is the grand total. What's the grand total? Grand total of all the houses you can build. 12, I think 12, right? Because it's the 6 and the 4 and the 2 added together. So I've got n is equal to 12. Then I have to single out each one of those. So the 1-story I'm going to label as n1. The 2-story I'm going to label as n2. And the split level I'm going to put as n3, or n sub 3. So 12 is n, so that's the total. N1 are all the 1-stories, N2 are all the 2-stories, and 3 are all the split levels. There it is. And now let's use our formula. So kind of careful with this formula. Put it together just a bit here. So the formula will look like this. Right, 12 is the total. There's an n on top. We're going to divide it by 6 coming over here, factorial, 4 over here, and then 2 over here. I will say this real quick here. Put an extra parenthesis on your denominator. Put a big old parenthesis here on the 6 factorial, another big old parenthesis here on the 2 factorial. All right, let's try that first. Try yourself, see if you guys get 13,860 yourself. That is not perfecto. All right, now I have lines. Okay, so tell me, let's see, I'm gonna do it one way, so you guys did it that way, okay? So one way to do it is 12. Factorial of math menu, come across probability, come across, okay, divided by. I'm gonna stick in a parenthesis right here. So now you go, is it 6? Is that right? 6 factorial? And you can either choose the arrows. Notice I can move with the arrows like this if I like. Or what I can do is I can actually choose the number 4 over here. Just click on this 4. Times. How many 2 stories? 4. 4 2 stories? 4. Probability. Times. I think there's 2 split levels. 2 split levels. Close it off and roll it off. 13,860 different combinations that can put those guys together. Different from any different. Anybody did any other different than that? I have the registry. Okay. Yourself, okay? Tell me you're done. Take a minute. Okay. Let's see which one did you do. Okay, sure, that's fine too. Sweet, still got it. Which way things easier? Oh, okay. Sure, yeah.
Yeah.
Okay, just real quick here, show again, just how I did it here, for the screen. Good screen, so we got 12 on top. We got to go to that factorial button. So the math menu. Over here, number 4, click. Then you divide by, and then all these guys have to be in their denominator. So to keep stuff inside a denominator, you click parentheses. So 6, I believe, is that right? Yeah. And so for probability, oh, so fun tricks. You guys ready for fun tricks now? 4 is the next one?
Yeah.
4. Go to math menu and go to the right. Oh, love it. And instead of scrolling down with the arrow button, just click on number 4. That's what those buttons are for, because it's a selection button. So click 4 times 2 math left 4 close parenthesis. Wow. This one, okay. Jam, are we done? Yeah, so we had something called permutations. Now we have something called combinations. First thing we should know is this right here, is the fact that combinations and permutations, they always get mixed up. Like, which one am I doing? So think about permutations that have order inside them. Combinations is you're just selecting certain objects. You don't care the order they come in. You're just going to have that group for yourself. So n selection, here is our formula. Very similar to permutations. NCR, n factorial is on top still. You have the n minus r factorial as usual. Then you have this extra little r factorial right here. Just there, just hanging around. So what happens here is the fact that order does not matter. So whenever I think of permutations, I guess in my mind, see if this helps you. Permutations is kind of like picking for 4 people, right? But then saying, okay, the first one's going to be president, the second one's vice president, the second one's the chairman, and the next one's the treasurer, right? So once you pick that first person, he actually has a specific job, so order matters on that, right? For combinations, it's kind of like out of the 10 people, we're just going to pick 4 people. The order now doesn't matter as long as you sort of have those 4 people, they don't belong in any order. So the race cars, right? Out of the 33 race cars, first place would be very much different from second place. Second place very different from third place. That's a permutation. So position matters. Combination, position does not matter whatsoever as long as you have your 5 objects, 3 objects, or 4 objects. So here it is. Finding the number of combinations can happen for the state departments of transportation. Wants to develop a new section of the highway and receive 16 bids for the project. The state plans to hire 4 companies. That's it. They're going to hire 4. Doesn't matter which order they come in on. It doesn't matter. But they're going to have 4 companies do the work. Now the question is, how many different possible combinations can 4 companies be selected from 16 companies? Let's try it. Let's try it. We have this combination thing, right? So the question is, does order matter on the companies? Does it matter which company is picked first? No, forget it. Okay, so it's combination. Let's go with it. So that means n is 16. R is equal to 4. And this whole concept of order is not important right here. All right, you guys, I think you guys have seen this little button. If you guys went to probability, underneath the NPR, there's also an NCR. Hey, what do you know? So underneath the probability button. So going over here, you should find an NCR button on your calculator. That's exactly what that is. So put 16 in first, put 16, put an NCR in the 4. Let's see if you get 1,820 is perfecto. Okay. Yeah, I'll just walk around just real quickly here. Sound good, ready? Yes. Awesome. Before tell me you got it. And got it over here, you guys got it. Yes. All right, let's use the calculator to do our number crunch. That's it. Got it? Sweet. Awesome. Okay, order does not matter. That's cool. Okay. So just a quick review. Fundamental counting principle, we just keep on multiplying things together right as they occur. That's the multiplication principle we've learned. We learned this little factorial button. We learned if order does matter, we're going to do permutations. If order does not matter, we're going to use combinations. Are we good there? Sweet. Okay, now let's dive into, I'll just tell you this here. We have 7 more slides left. Okay. Now let's put in all the probability stuff. So we learned permutation just kind of gives you the possible combination, right? So let's jump back and let's put this all together into probability. So student advisory board, if you want to just write down 16 members if you want. 3 members serve as the board's chair, secretary, and webmaster. Each member is equally likely to serve on the position. So now the question is, what's the probability of randomly selecting the 3 members who will be chosen for the board? So again, notice we're back to probability now. Okay, so let's jam. First things first. Is order important? I think so. What are you guys saying? Because the person that's selected, they're selected, one of them selected to a chair position, right? One of them selected to a secretary position, one is selected to a webmaster position. So order does matter as they're selected. First one's gonna be the chair, second one's the secretary, and third is gonna be the webmaster. Okay, since order is important, there's only one favorable outcome. So let's see if this makes sense here, right? So it's a permutation or hence. So 17 is going to be first. 3 positions here. And I'll wait for that one. And so if you guys get to 4,080 real quickly here. You guys are masters of that. Just think of this. Isn't this kind of crazy? You guys walked in today not knowing those things what you use on the calculator. Yeah. And those functions of the calculator. You walked away knowing some cool stuff. Okay, everybody got to 4,080. Good. Problem. Okay, good. Remember, it's a permutation, right? It's a permutation. Yeah. I will trust you more and more as you guys get there. Old fashioned one, all right.
Is there a button?
Yeah, so let's go with put in 17. Go to math. Go to NPR number 2. Sure. And Uh-huh. So you got an NPR button, Kimberly, and you have a combination button. They're right next to each other. Okay, now, question is this, what's the probability of this happening? So here it is, guys ready? P of, this is the big one right here. This is what we went to. We want to get to the 4,080 just to be our denominator. So 4,080 are the number of possible ways this can happen, right? It's our denominator for probability. So what's the probability of selecting the three members, those particular three members? It's going to be 1 out of 4,080. Are we good? Very, very low probability, yes, for one of those possible outcomes. We should bring in like the California model, because this is kind of where this falls into, like all the different combinations. And then what's your success variable here? Okay, let's go a little more here. Got like two problems or three problems. Let's see. So find the probability. Remember, it's going to be of being dealt 5 diamonds from a standard deck of 52 plain cards. 5 diamonds. So remember, if it's a king of diamonds, queen of diamonds, who cares, right? It doesn't matter as long as it's a diamond suit. Find the probability that we dealt with 5 diamonds. So you're going to get a 5-card draw on your hands. Somehow all of them turn out to be diamonds. That's cool. Okay. So first things first is how many diamonds do we have in a deck of cards? I don't know. I'll wait for you guys. Let's see, it's 52 cards, right? There's 4 different suites. So on the calculator real quick here, if you divide 52 by 4, that will tell you 13. 13, okay, cool. So there's 13 cards per suite, right? So there's 13 cards of hearts, 13 cards of diamonds, 13 cards of clubs, right? And 13 cards of spades. Okay, real quick here. Combination or permutation? Talk to me about this guy. Combination or permutation? Two. I'm going to go with Giselle combination, right? And it's combination because it doesn't matter which card is what, right? It doesn't matter if I'm handed diamonds in the first round, in the second round, and third round. So it will be, guys, it should be a combination on our hands, right? It should be 13 out of 13. Choose 5 combinations out of 13, right? Or 13, choose 5. Okay. Can we get that one? So find me 13 NR and CR5. Sweet, what we get? Perfect, okay. And so 5 diamonds, right? We have 1,207. So this is just the number of diamonds, right? So now the question is, what's the number of, and it's over here already because I couldn't do it right. What are all the different possibilities of choosing 5 cards from the deck of 52 cards? That's the next question. So it'll be 52 combination 5. Okay, now it's going to be the division between those two. Good. That's so cool. Okay, hold on. I'm going to go with that here. some people, when they move, but when they got in the calculator, it was like something like this right here. When they did this right here, they got 4.95, blah, 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 right? And at the end, it says E, -4. Anybody else got that in the calculator? Sweet. Okay. What this means is it's this decimal has already been moved over 4 times to the right away. So you have to move it 4 times to the left in order to compensate. Okay? So it's going to be like this right here. This is 4.95. Because you have the -4 here, which means 1, 2, 3, 4 is your correct decimal point if you need to put it to standard notation. So there it is, 0.000495 if you want to do this 5 somewhere in that range. Are we good? That was good. Okay. I think that's the last problem is pieces still here. Okay, let's go. Food manufacturer, analyzing a sample of 400 corn kernels. And then they wanted to just test for toxins. They do this with water all the time. In this sample, 3 kernels have dangerously high levels of toxin from unused fertilizer or something. 4 kernels are randomly selected from the sample. What is the probability that exactly 1 kernel contains a dangerous high level of toxin? So let's see. Funny question, right? Because we actually know how many of there are, right? But then what's the probability of selecting them? What we will do in real life is we go backwards. So if we're only selecting 400, we got this probability of dangerous toxins, how many are in our sample? And eventually it says how many are in the population, if that's true. So in the sample, 3 kernels have dangerously high levels of toxins. We know that for sure. So 3 out of the 400. What kernels? 4 kernels are randomly selected from the sample. Probably that exactly 1 kernel contains dangerously high levels of toxin. Let's jam. So the number of possible ways of choosing 1 toxin kernel out of the 3 toxin kernels. The number of, again, this is going to be a big problem here. Oh, now you think you should have put me to break, huh? Now, yeah, that was too much now. That's okay, last problem. So let's go through this one at a time here. Let's see. So, possible number of ways of choosing 1 toxic kernel out of 3 toxic kernels. There's 3, huh? Because there's only 3 of them, right? It's a combination of actually 3 choosing 1. Possible ways of choosing 3 non-toxic kernels from 397. That one right here. So 397, choosing 3 of them, so that means no kernels are toxic whatsoever. We're kind of putting a lot of stuff together, putting the multiplication principle, now with the combination stuff. Using the multiplication principle, the number of ways of choosing 1 toxic kernel and 3 non-toxic kernels is, let's see. So choosing 1 non-toxic toxic kernel, then choosing 3 other ones that are non-toxic, because you have to choose not from the 400, you got to choose from the 397, the non-toxic kernels. It'll be 3 times that. So now 31 million different possibilities. Notice the equations are kind of like stacking on top of themselves. That's going to be the tough part of the homework, especially when you get towards the end. Now you have probabilities that are sort of coming together and trying to think, okay, which am I using the multiplication principle? Am I not? Okay, talk to me written down. So now finally here, the number of possibilities of choosing 4 kernels from 400. Right, that's going to be our denominator, right? This is just choosing them in general, right? We're going to choose 4 from 400. This is the probability of all different possibilities. And then finally, here it is. Probability of choosing one toxic kernel is this. Out of the 3 that we chose, one was, I'm sorry, out of the 4 that we chose, right? One was toxic. The 3 other ones were not toxic. Over choosing 4 altogether. And it's about 0.03. So what is that? About 3%. Possibility about 3% possibility. All right, how about this? I'm gonna leave this up right now. Can we go into something kind of mind blowing? Sure. No, Andrea says easy stuff.
No.